Physics worked great until tiny things broke the rules. For a long time, the world looked predictable. Throw a ball, it follows a path. Push a swing, it swings back. Heat water, it boils. Classic physics is the reason bridges stand, engines run, and your phone doesn't fall through your hand. It's a rule book built for everyday life, and it works insanely well. But then scientists started looking at the very small, atoms, electrons, light, and suddenly the old rules didn't just bend, they stopped working. Around the early 1900s, a few experiments refused to make sense. Max Planck found that energy didn't behave like a smooth stream. It came in little packets. Then Einstein showed light can also behave like packets. Photons. Like tiny paintballs of light. And once people started studying atoms, it turned out electrons don't move like little planets around a sun. They follow a totally different rulebook. Bohr, Schrödinger, Heisenberg, all of them made a huge impact. The point is, the smallest things didn't play by the everyday rules. That new rulebook is quantum physics. Classical physics says if you know enough about something, where it is, how fast it's going, you can predict what it will do next. The future is basically a calculation. Quantum physics says even if you know everything you're allowed to know, you still don't get a single guaranteed outcome. You get probabilities. A simple comparison, classic physics is like a train timetable. If you have the schedule, you can predict where the train will be. Quantum physics is more like weather. You can be highly accurate, 70% chance of rain. But it's still an odds-based prediction. Casinos run on probabilities. Insurance companies run on probabilities. Weather apps run on probabilities. Quantum physics is the universe's probability engine at small scales. So what is quantum physics actually describing? It describes something called a quantum state. A quantum state is basically the best description you can have of a small system, like an electron, before you measure it. If I hand you a sealed mystery box and ask, what's inside? You can't say exactly, but you might have a list of possibilities. The box might contain a coin, a key, or a battery, and based on the shape and weight, you can assign odds. A quantum state is like that, except it's not just guessing. It's a precise mathematical description that tells you the allowed outcomes and the probability of each one when you measure. Now we hit another major quantum concept, superposition. Superposition means that before you measure, the system can have multiple possible outcomes still in play. The quantum state contains more than one possible answer to your question. It's like ordering at a counter when the menu is still open. Before you order, multiple choices are genuinely available. Burger, salad, pasta. The restaurant hasn't started making anything yet. The moment you place your order, one option becomes real in the only way that matters. The kitchen commits. Quantum superposition is that idea, but in nature, multiple outcomes are possible, and the state carries those possibilities together. In the quantum world, finding out isn't free. The moment you try to get a definite answer, you can change the system so much that the answer you get is no longer what it would have been without the check. When the quantum system bumps into something, a detector, a screen, a sensor, in a way that forces it to produce a definite outcome and record that outcome in the environment. Here's a real-life comparison, checking a cake by opening the oven. You open the door to see how it's doing, but you changed the temperature and airflow. You didn't just observe, you interacted. The result you get after that might be different because you checked. In the quantum world, checking is never neutral. To get an answer, you have to interact with the system, and that interaction is part of what creates the outcome. So the rule is, in quantum physics, measurement doesn't reveal a pre-written answer. It helps create a definite answer. Next, the uncertainty principle. Instead of thinking of uncertainty as scientists aren't sure, think of it as a built-in limit, like the universe setting a boundary on how sharp your answer can be. It means there are certain pairs of properties, like position and momentum, that cannot both be perfectly sharp at the same time. The rules don't allow it. Here's a simple camera comparison. If you try to take a photo of a fast-moving object, you can choose a very fast shutter speed to freeze it, but then the image gets darker because less light comes in. Or you can let in more light, but then motion blur increases. You can't maximize both at the same time. There's a built-in trade-off. Quantum uncertainty is like that. It's not, we don't know because we're bad at measuring. It's, you can't have infinite precision in both at once. That trade-off is baked into the way quantum states work. Next, quantum entanglement. If superposition is the multiple options idea, entanglement is what happens when those options get shared between two things. So they stop behaving like two separate systems and start behaving like one combined system. Entanglement happens when two particles share a single combined quantum state. Instead of each particle having its own separate instruction sheet, they share one. So when you measure one particle, the results you get are strongly linked with what you'd get if you measure the other, even if they're far apart. Entanglement is not a cosmic walkie-talkie. You can't choose a message on your side and make it appear instantly on the other side. If that were possible, we could beat the speed of light, and physics doesn't allow that. What entanglement gives you is a link in the results, not a way to transmit a signal. What entanglement gives you is correlation that are not explainable by regular physics. Here's a simple comparison. Imagine I put two gloves in two boxes, a left glove and a right glove. I send one box to you and one box to your friend across the world. The moment you open your box and see a left glove, you instantly know the other box has the right glove. That's a correlation. But that glove story has a hidden assumption. The gloves were left and right from the beginning. The outcome was pre-written. Quantum entanglement can violate that kind of pre-written instruction explanation. Experiments based on Bell's work show the world can produce correlations that can't be explained by local hidden instructions in the way the glove story can. So the safest, simple takeaway is, entanglement means two systems act like one shared system even when separated. It's a link in the state, not a signal in space. So why don't you see quantum effects when you toss your keys onto a table? Because the everyday world constantly touches everything, and that ruins the delicate quantum behavior almost instantly. Because quantum behavior is fragile. Quantum effects survive when a system is isolated. But your everyday life is not isolated. It's loud. Air molecules bump into everything. Light hits everything. Heat spreads everywhere. Your environment is constantly stealing information from systems. That process is called decoherence. And here's the simplest way to think about decoherence. It's like trying to hear someone whisper in a loud party. The whisper is real, but the noise overwhelms it. The clean pattern gets washed out. Decoherence is why big objects act classic, not because quantum stops applying, but because the environment destroys the delicate quantum conditions. So classical physics is not wrong. It's what quantum physics looks like when you can't keep things perfectly controlled. Now, let's connect this directly to your life. Quantum physics isn't just something happening in expensive labs. It's the reason modern technology exists. Semiconductors, the chips in your phone and laptop, work because electrons in solids follow quantum rules. LEDs and lasers are quantum devices. They rely on electrons jumping between specific energy levels and releasing photons in controlled ways. MRI uses quantum properties of atomic nuclei, spin, to create images inside your body. Atomic clocks are quantum technology. The precision timing behind GPS and global systems relies on quantum transitions that are incredibly consistent. That's it. That's the playbook. If you like the video, subscribe for more quantum stuff.